make sure that we know the proper way to do that. So, if you have a plot like that and you want to know what the instantaneous rate is right at that point right there, well, it's defined as, the rate is defined as minus 1/3 dO2 dt, right? Based on the fact that we're given what the plot of the oxygen is. Okay, and this is the slope at that point right there. So the way I did this problem is I kind of made a straight line. You didn't have a straight edge, but and so I was very lenient about that part of it. All right, so the rate then would be minus 1/3, and then I need to come up with a value for the slope of that line, which, you know, the tangent of the curve at 15 seconds. So it's going down from, you know, well, this decreases along there, so that's going from 0 to 0.65, and that's a negative, minus 0.65, and out to about 35. All right. So that is the way to calculate the instantaneous rate. All right. So from the balanced equation, you get for the concentration that you're looking at, you get what the relationship is between that concentration and the rate, and then find what the slope is at that point, and use that for its in that relationship right there. All right. So if you see that again, then you'll know how to do that problem, I hope. Most people did pretty well on the rest of the problems. If you didn't, you can always look at the key, but I did want to emphasize this one. There were some people who didn't know how to look at these graphs to determine the order, right? So concentration versus time, if this one's linear, that means it's zero order. If it's log of concentration versus time, and that's linear, then it means it's first order. If 1 over the concentration versus time is linear, that means it's second order. So in this particular case, of those three, the one that follows the closest straight line is the log plot, which means it's first order for the order. All right. Then the k, the slope, is equal to minus the k. All right, so there's the slope, and that negative sign should not be there when you report the rate constant, because the negative of negative gives you a positive number. Rate constants are never negative numbers. Right? So a lot of people made that mistake. So it's 0.0198, the value. A lot of people didn't get the right units on this. Right? So if it's a first order process, that means n is equal to what? 1, right? There's only one reactant, and so the sum of the orders is equal to 1, and we know that the units are molarity to the 1 minus n, seconds to the minus 1. So what does that give us for the units?
1 over seconds.
Yeah, inverse seconds, or 1 over seconds. So got to make sure you don't have a negative sign there. Make sure you use the right units. All right, so it's very possible. Don't guarantee it, but it's very possible you'll see another problem like that at some point. Those are common questions we ask on common exams. All right, so we've got a little bit more to do on chapter 14. Explain how enzymes act as biological catalysts and how they interact with specific substrate molecules. All right, so right here in the learning objective, realize an enzyme is something that works inside a living organism and is a catalyst. Right, so it's a biological catalyst. It speeds up chemical reactions. Anybody know what kind of molecule an enzyme is? It is a protein, which is made up of amino acids. Right, so you have all these amino acids that combine together in a particular arrangement, primary structure, to give you this protein. So an enzyme biological catalyst, and it is a protein made up a whole bunch of amino acids. So these are huge molecules, sometimes tens of thousands of grams per mole, right? So I'm going to illustrate that with this really big chunk here, and then I'm going to put a little piece like that. All right, so here's my enzyme. And then you've got a substrate molecule that's supposed to, there's my substrate. And then there's this thing right here. This part of the enzyme is called the active site. All right, that's this huge molecule is arranged in such a way. And how are the three-dimensional arrangement of those atoms in those molecules are held together by what? Anybody remember talking about proteins? Like if you have a tertiary structure and then like a helix or pardon me?
I don't know.
Okay. So anyway, these molecules are in these different shapes due to hydrogen bonding. Right? The intermolecular forces from one side of the molecule to the other puts it into just the perfect shape so that it forms this active site that the chemical reaction that needs to be catalyzed will come and fit right into that. Right? And so normally what happens, that active site doesn't fit exactly. It actually kind of stretches it out such that then the bond can break and then either react with something else or if it's just one thing, then the intermolecular forces, once it fits in there, the intermolecular forces of that molecule pull the rest of it apart. All right, so the point is that there is this protein that has a specific shape due to the hydrogen bonding that's involved from one side of the molecule to the other, and that the substrate fits right in there. All right, so that speeds up the chemical reaction. In other words, that substrate, if it encounters, if for instance it has to react with water, right? The water and the substrate fit right in there, and then it goes on to react. If the water comes in contact with the substrate, the probability that it hits it right in the right place is very small. This puts the reactants right in the right position, plus it stretches out the bonds a little bit so that it speeds up the reaction millions of times faster. All right, so hopefully if you remember from last week, for most chemical reactions, what does the rate do as you increase the temperature? It increases, and it's like a linear increase. Actually, most likely not. It actually goes up dramatically. Right? It's an exponential increase based on the Arrhenius equation. All right. So what does the so this is for a normal reaction. All right, what does a enzyme catalyzed reaction look like for its rate versus temperature? Well, we get the increase like that. Anybody know what happens after that?
Slows down.
It actually peaks at some point and then goes down like that. Okay, so there is a maximum, and for like the enzymes in our bodies, where's the peak in that the temperature? 98.6 degrees Fahrenheit. That's right. Right. So there's a peak. Right, you go much above that, and then the reaction rate goes almost to zero. Right. So why is that? Why is it that it's unusual? Most reactions, it just keeps going up. But with an enzyme catalyzed reaction, you get 5 degrees above there, and it basically drops to zero. Yes,
doesn't the high temperature mess with the structure of the protein?
Okay, that is correct. That these proteins are held together by hydrogen bonds, and as you increase the temperature, those hydrogen bonds start getting broken, and so it changes the shape of the protein. All right, and what happens when the shape of the protein changes? The active site changes shape, and now the substrate no longer fits inside there. All right, so that's called denaturing. 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 All right, so or denatured. All right, so temperature increase causes the protein to change shape and, all right, and let's say and the active site deactivating the enzyme. All right, doesn't cause the chemical reaction to occur anymore, because in order for the reaction to occur, the active site has to have a specific shape. As you increase the temperature, the protein changes shape, causing the active site to change its shape, and therefore it no longer will catalyze the reaction. Right? So that's denatured. Then the protein can be denatured. Now, if you don't have, you have small temperature changes, right? Then you reduce the temperature, then it can change right back. But if you get too high of a temperature and the thing actually starts cooking, right? Then you get permanent changes, and so the enzyme will be permanently deactivated, right? So, if you're familiar with eggs, right? They have proteins in them, and when you cook the egg, you notice a very big change in cooking when you cook an egg. Do you think you can denature that? You can put the protein back from that denatured state? Not that I'm aware of. So that would be an example of being permanently denatured, right? But if you ever encounter a medical situation where somebody you're near starts getting a very high temperature, 104, 105 degrees, right, that's very dangerous, right? And you need to actually help that person out. What would you do? Yeah, well, put them in a cold ice water bath, right? Or if if it just snowed outside, you stuff them into the snow or something. You have to do something to bring that temperature down, right? Because if you don't, right, then all the enzymes are deactivated, and then the chemical reactions that are required for, a living person then no longer happen, and then that can cause death. So if your body temperature gets too high, then it's possible you will die. Right? So that's heat stroke, right, if you're familiar with that. Okay, so I think we've covered everything we need to there. Explain why enzymatic reactions respond differently to temperature changes compared to non-enzymatic processes. Right? So we just went over that. Now, part of this, the learning objectives includes chemical warfare. All right, so I've got some slides that I'm going to show you about how nerve agents cause problems in biological species. Right, so here's a actually, this actually has some chemical compounds. Right, so you can see these are chemical warfare agents: phosgene, hydrogen cyanide. What's not included on here was the very first one that was used, I guess, historically speaking, in the modern age. Anybody know what the first chemical warfare agent that was used? Chlorine gas. That's right. In World War I, in Belgium, right, the Germans had a whole bunch of tanks of chlorine gas, and when the wind got in the right direction, then they opened up the tanks of chlorine gas, and so in the trenches they killed a lot of people from that chlorine gas. All right, that's an example of a choking agent, chlorine. Right, so with a choking agent, you breathe it in. Right, so it then decomposes or kills the cells in your lungs, and they start secreting liquid when that happens, and then you basically drown from the liquid that is secreted into your lungs, right, from yourself. Right, so phosgene does the same thing. It destroys the lung tissue, and so you end up dying from that. HCN, hydrogen cyanide, cyanogen chloride, those are blood agents. Right? And I used to live in California. I grew up in California, and back then when I was a kid, they had the death penalty, used it occasionally, and that's what they used was hydrogen cyanide it's a gas they release into the room, and then the person would breathe it in, and it would kill them because it prevents the oxygen from in your blood from being transmitted to the cells where oxygen is needed for energy production from your cells. All right, so I think I've got a list with the learning objectives. We've got recognize selected classes of toxic agents, blister agents. If you've heard of mustard, that was used. That's been used in warfare. I think Iraq used it in the Iran-Iraq war. And it's a pretty simple compound. It's got a sulfur in the middle, and then it's got 2 ethyl groups, and on each of the ethyl groups it's got a chlorine. Right? So, and man, those things stink. When I was doing research in organic chemistry, I used a sulfur compound. It had 2 sulfurs instead of 1. And it didn't have chlorine, it had OHs on the ends. But man, you open that thing up and it's stunk terrible. So anyway, if you get a blister agent on you, on the surface of your skin, right, then it will burn away the cells, right, damage the cells, and so you get these big blisters forming. If you want to see some really gross pictures, go online, and Google blister agents, and you can get some photos of people who have had blister agent applied to them. Then there's these ones that have phosphorus in them. Right? Those are the nerve agents. That's what's common in nerve agents is a phosphate group, which is replaced with, let's see, there's a fluorine there and a methyl group and organic groups. So these are organophosphate type molecules. So if you see a phosphorus, right, then it's going to be a nerve agent. And so let's see, that's GB, so sarin, right? So that's the one we're going to talk about in terms of its effect on how that affects your central nervous system. I'm not really familiar with GD. VX. So these two are normally transmitted through the air, right? So they're vapors. They're liquids with high vapor pressures, and so they are used as airborne nerve agents. VX is a viscous liquid, right? So you have to actually get that on you. But so you breathe these in, or you get VX on the surface. So if you don't have to actually ingest a nerve agent, if you get it on your skin, it will be absorbed through your skin into your bloodstream, and that will still kill you, right? So it's absorbed through the skin. And so they're very dangerous. Takes about the size of a pinhead, right, to get on you to be a lethal dose. So it doesn't take very much of these things. And then these things right here, CN and CS, those are riot control agents right there. Those are the riot control agents. So tear gas. And these things, this table is on the chemistry department website. There are a few more, but I think let's just make sure that we've covered everything, which I think we have. So you've got a mustard and lewisite, which are blister agents. Get them on your skin. They're not normally thought of as an internal hazard because they're liquids. But if you did actually get some inside of you, that would be very damaging too. But normally it's just on your skin that is how you'd normally encounter those. By touching something or having a spray. Well, if it's a spray, then you can breathe it in. But it is a viscous liquid. So those are blister agents, nerve agents, right? The phosphorus with the sarin or the VX. Choking agents, chlorine, blood agents, HCN, and riot control agents. The CS and the CN. So we've seen each of those. Does anybody have any questions about that, which I may or may not be able to answer? So there is a chemical warfare treaty where theoretically, right, all countries, a large majority of countries have signed it, right? So we're not supposed to use these in warfare, which is a good thing, I would think. So now, as far as the mechanism by which a nerve agent works, I have some transparency case study of nerve agents. And you are responsible for understanding this. That was the very last. Explain the mechanism by which sarin inhibits acetylcholinesterase. So anybody know what acetylcholinesterase is? Yes?
Is it related to acetylcholine, which is the main neurotransmitter in your parasympathetic nervous system?
Okay. Sounds like you know a lot about this. Good. All right. So acetylcholine is what goes in the synapses, and then acetylcholinesterase is it's an enzyme that then decomposes the acetylcholine that's in the gap in the synapse. Right. So. Okay, so essential neuromuscular junction removes excess acetylcholine from the synapse, allowing the neuron to reload and fire. Right. So when your brain sends a signal to your foot to move your foot around, right, that electrical signal has to pass through nerves. Right. The nerves are separated from each other by a gap, which is called a synapse. Right, so there's the synapse. And it's hard to see the red stuff in this, but we'll do the best we can. I plan on sending this out as a PDF file. I'll scan it and send it out to you. But so the brain sends a signal to the foot, right? There are these synapses, and when that signal, the brain sends that signal, acetylcholine goes into the synapse to allow the electrical signal to pass. All right. So at some point it needs to stop sending the signal, right? And that's where the acetylcholinesterase is. It's an enzyme which catalyzes the decomposition of the acetylcholine. All right. So acetylcholine, acetylcholine is a reasonably simple molecule. Okay. There's acetylcholine. Right. So it's just got an ammonium group and then an ester group, which talked about an amine group that's been protonated. Actually, I guess it's been methylated, and an ester group. And so right here is the ester linkage, and so that was made by a condensation reaction. Remember that condensation reaction? Well, what acetylcholinesterase does is it reverses that condensation reaction. It breaks that bond right there, and it reacts with water to give you an acid, acetic acid, and then an alcohol group over there. Right. So that's what acetylcholine looks like, and so what happens is acetylcholine goes in there. And here is the acetylcholinesterase, like a little Pac-Man thing, goes in and reacts with the acetylcholine to break it apart, right? And when it's broken apart, it doesn't transmit the signal, right? And so it removes the acetylcholine so that the next time a nerve transmission comes about, then acetylcholine goes back in there, right? And so that's how nerves work. And so there's the reaction. And this is terrible because you can't see the red. There. So anyway, so this is the reaction that gets catalyzed by the acetylcholinesterase, is the water reacting with acetylcholine to break that bond right there. And so produces the acetic acid and then an alcohol group right there. And that doesn't then transmit the signal. Okay, so what happens is that acetylcholinesterase has an active site that has this amino acid serine in it, and the serine has an OH group on it. So this thing right here, that's supposed to represent the nerve agent coming in and reacting with the OH group on the serine, and that's a covalent bond, so it permanently deactivates it. Right? So there's the active site, right? That it comes in and attaches to the acetylcholinesterase and then deactivates that. Right? So what happens is, here's what the serine reacts. Here's the OH on the serine, reacts with the phosphorus, splits off a fluorine, and then binds covalently to the enzyme. So now that big molecule is sticking in the active site, and so the acetylcholinesterase and water can't get in there to react. And I guess the last thing, or these are some of the different ones, which I guess we showed before. All right, so that's how nerve agents deactivate acetylcholinesterase, the enzyme that catalyzes the destruction of the acetylcholine in the synapse. And so if you are a victim of nerve agent poisoning, you get some on you or you breathe it in, what's going to happen to you?
The synapses are going to fire.
But they're going to continue to fire. They can. That's why you get all tense and it's continually firing, and so you can't stop them, right? So, and that will eventually cause death in a few minutes, if you get a lethal dose. All right, and that's all our learning objectives for the kinetics experiment, kinetics chapter. Yes.
Sir, how would you stop the serine from attacking? If you were a victim of the attack.
All right. So normally you protect yourself with a suit. All right. Now, if you actually did get some nerve agent, then there are two antidotes, right? Which you take these things, you jam them into your knee, into your leg, and so one of them replaces goes in and removes the nerve agent out from the acetylcholinesterase. The other one actually reacts with acetylcholine, right? So it acts as a replacement until the body can regenerate the acetylcholinesterase from the other one. So there are actually two things that I remember one's called 2-PAM chloride, and I can't remember what the other one is off the top of my head. Right? But there are some antidotes as long as you don't get too big a dose. Right? If you get a very large dose, then just lay down and die. There's nothing you can do about it. But the Navy does have inventories of chemical biological warfare suits that are available if, for some reason, we encounter an enemy who might possibly have chemical weapons. Right? It's very difficult to move around in those things. Right? I was in the Naval Reserves and went to a chemical biological warfare unit, and I probably should review this, everyone. This was 20-something years ago. And I actually did put on one of those suits, and I don't know, anybody from Alabama? Do they still have the chemical warfare in Anniston, a base in Anniston?
They might.
Maybe. But that's where I went, one 2-week period for training, and they made me put on a suit and actually go into their room where they then released some sarin, right? So that was to show us that the suits actually worked. So yeah, they actually had live training of that stuff. And I've put on the suits, and they're very bulky. They're very difficult to move around in. So it's not something that you'd want to use, but it's something you would want to use in the case of somebody using some kind of chemical biological warfare agent. Right? So
Are those agents hard to engineer?
Hard to synthesize, maybe safely. I'm not familiar with the nerve agents. I think any good chemist can pretty much make them because, I mean, they're molecules. You just have to follow the recipe. Some of those molecules are very easy to make. I mean, I could go into the lab downstairs and make chlorine or phosgene or stuff like that, or mustard. But I'm not familiar with how to make the nerve agents. But I'm sure that they're not that difficult. But the point is you have to do it safely, right? As soon as you make it, if you then get some on you or it goes into the air where you're doing it, then that could be a problem. All right. Mr. Karaher, you're our new section leader. And our old section leader is not here to give you the sheet, but we'll have to make sure that happens on Thursday. All right, let's press on. All right, so I passed out a worksheet, so we're actually going to start a new chapter. We're not going to get to do that worksheet right away, but have that in the ready after we discuss the introductory part of equilibrium. All right, so this is the last chapter before the 6-week exam. All right, so the 6-week exam will have chapter 13, 14, and 15. So colligative properties, solutions, then kinetics, and now equilibrium. And that's all that's going to be on the 6-week exam. All right, so if we have a chemical reaction, A plus B goes to form C plus D. All right, so just making it simple, one to one there. If we make a plot, if we start with no reactants, no products. We've got reactants, but no products. All right, so this is time. All right. Then what happens is the reactants will start to go down. Products will start to go up. Okay, now, depending upon what the equilibrium constant is, let's say that it goes fairly far to the right, then, but doesn't go 100%. In other words, as products build up, then they can collide with each other and go in the reverse direction. So we're going to now have double arrow here, meaning that we have reactants colliding, going to form products, because as products form, they can collide and go back in the reverse direction. And so you can reach a point where it levels out, where when the concentrations stay constant with respect to time, in other words, they're not changing anymore, it reaches what's called equilibrium. And that's, in order for that to occur, the forward rate and the reverse rate have to what?
Equal each other.
Be equal, right? So that's what equilibrium is. It's a dynamic process. Now, what does that mean? There's something called a static process, and there's something called a dynamic process. Static process means nothing moves, right? If you've got a little balance there and you put two weights on it and it's stationary, right? That's a static equilibrium. Right now, if you put something on one side, then it will go down and the other one will go up. But if you got two weights, they are stationary, right? Then that's static. Dynamic would be, as in a chemical equilibrium, is that you continually have things changing, where you have some of the reactants are continually forming products, but you have the same number of products that are going back to form reactants. So things are changing within the system, but they're reacting within the system, but the net effect is that there's no change. Right? So it's a dynamic process where the forward reaction rate equals the reverse reaction rate such that the concentrations do not change with respect to time. Change with respect to time. All right. So in this example here, we mix the reactants together, and then the concentrations are changing, right, as the reactants go down and the products go up. But there will be a point at which it reaches an equilibrium, the two reaction rates are equal, and so the concentration doesn't change. All right. I hesitate to ask, do you want to see a kind of a simple derivation of what's called the equilibrium constant? Or do you just want me to put it up on there? Just put it up. Let's just put it up. All right. The equilibrium constant, K. Okay, so this is for the generic process AA plus BB goes to form CC plus DD. All right. So the equilibrium constant is defined or can be derived as being the concentration of C raised to the C power, the concentration of D raised to the D power, divided by the concentration of A raised to the A power, concentration of B raised to the B power. That's what we call an equilibrium constant. I don't want to deviate too much from what I did before. All right, and so those are the concentrations just raised to the powers. All right, and this occurs when the rate of the forward reaction equals the rate of the reverse reaction.
That's when you can only use this equation?
Yes. If you haven't reached equilibrium yet, then you can't use that equation, right? And so in this case, the concentrations are in moles per liter. Moles per liter, or molar, right? When it's the case of C. We also have something called a case of P, where for any gases that are present, in other words, these don't all have to be gases, but for this case, we'll say they are all gases. Wherever there's a gas, we'd replace the concentration in moles per liter with the pressure. So it's the pressure of C raised to the C power, the pressure of D raised to the D power, divided by the pressure of A raised to the A power, and the pressure of B raised to the B power. That is the equilibrium constant in terms of pressure, equilibrium constant in terms of pressure. All right, so there, pressures used for any gases. And there's a relationship that the case of P is equal to the case of C, RT to the delta N, all right, where R is the gas constant, which is 0.08206 liter atmospheres per kilomole. T is the temperature in Kelvin. I should put absolute temperature in Kelvin. Delta N is equal to the number of moles of product gas. Let's see, moles of gas products. That's a better way of saying it. Gas products minus the number of moles of gas reactants. That's what delta N is. All right, so these things have numerical values where you can just look them up in tables. Right, so on the equation sheet, right, here represents an equilibrium constant K. This reaction of ammonia dissociating into ammonium ions, is 1.8 times 10 to the minus fifth. Here's aniline. Its equilibrium constant is 3.8 times 10 to the minus 10. So this is an ionization of these molecules in water to form products. Here's some equilibrium constants associated with barium fluoride breaking up to form ions. I can't even read that. 2.4 times 10 to the minus something there. So anyway, these equilibrium constants have numerical values, and their numerical value only depends upon the temperature. It doesn't depend upon the volume of the container, doesn't depend upon the pressure of the container, right? It only depends upon the temperature. So the value of the equilibrium constant for a particular reaction, I guess I should say, for a particular reaction, depends only on one thing, and that one thing is temperature. So the equilibrium constant values that I was showing you here, these are all for 25 degrees. These particular equilibrium constants would increase as you increase the temperature. We'll find out why that is next time. For now, you just have to believe me that these equilibrium constants go up with increasing temperature. Now, specific cases of delta N. All right, so let's say we've got nitrogen gas plus hydrogen gas goes to form ammonia gas. All right, what is delta N? If we had the value of K sub C for this reaction, and we wanted to get the value of K sub P, what would I use for the value of delta N in that equation right there? Okay, it would be 2 moles on the right-hand side, 4 on the left-hand side, so it would be 2 minus 4 equals minus 2. So delta N would be minus 2 there. Yes?
So, Professor, if you, for some reason, had a liquid product or reactant in there, you wouldn't count that in.
That is correct. In fact, I was going to do one example like that. But I want to do this one first. Right? So hydrogen gas plus chlorine gas goes to form 2 HCl gas. All right, what's delta N there? 0. It's 2 minus 2 equals 0. And so what does that mean when you have the same number of moles of gas on each side? What does that mean about K sub C and K sub P? They are equal to each other, right? Anything to the 0th power is just 1, right? So those two are equal when delta N is equal to 0. And now the other case. Let's say we had, let's see, I'm trying to remember the 2IF3 gas in equilibrium with I2 solid plus 3F2 gas. All right, so decomposition of iodine trifluoride. What would delta N be there if that iodine is formed, precipitated out on the sides of the container? 1. Okay, it would be 3 minus 2 equals 1, because we wouldn't count the solid. Only count the gases. 3 moles of gas there, 2 moles of gas there. Now, it turns out, if you look at these equilibrium constants, you might think they had units on them. Does that look like they would have units? For instance, if we had nitrogen and hydrogen on the bottom there would be concentration to the 4th power, and there would be ammonia to the squared power. So molarity squared divided by molarity to the 4th, right? Be units. Right. Well, it turns out that these equilibrium constants do not have units associated with them. The reasoning behind that is a little bit more complicated than what's necessary for this course, but it turns out that these concentrations are ratios of the measured concentration to the concentration when in its standard state. All right. So hopefully, last semester you talked about standard states, and hopefully you didn't get any wrong information about standard states. All right. But these concentrations or these pressures are ratios of the measured concentration versus what the concentration is for the standard state. All right, so there are different, and standard states depend upon the phase or the species that you're talking about. So there's a solid, there's liquid, there's gas, there's solvent, and there's solute. Those are the only ones you need to worry about. All right. Does anybody remember what the standard state? Right. Hopefully you talked about standard states when you talked about thermochemistry, because that little degree sign on the delta H. Anybody remember that little degree sign that goes there? That means everything's in its standard state. So what did that mean, standard state, for a solid? Actually, it doesn't have anything to do with either pressure or temperature, other than the gas has a standard state that's in terms of its pressure. But a solid, the standard state is the pure solid. That's what the standard state of a solid is. And its concentration is equal to 1. The reason for that is if you've got a solid, right? What does its concentration depend upon? It only depends upon its density and molar mass, I guess. In other words, if you have 1 liter of something compared to 2 liters of something, and it's a solid, right? Same solid. Does it have the same density? 1 liter compared to 2 liters. Yes, they have the same density. All right. Density is grams per milliliter, which if we just divide through by the molar mass gives us moles per milliliter. So what would we say the concentration between those two solids, how would we compare them? Are they the same or are they different? Is the 2-liter solid greater or less than the 1-liter solid? Its concentration in terms of grams per, or in terms of moles per liter. What is it, Ms. Kelly? They are exactly the same. That's right. Right? The 2-liter has twice as much moles as the 1-liter does. So the moles divided by the volume is the same for both of them, for a solid. Right? So all solids have the same, all solids of a particular substance have the same concentration, whether you have a small amount or a big amount. Doesn't matter. Right? And so what chemists do is they say, all right, if C is a solid, is that concentration ever going to change? No, it does not, because it doesn't matter what volume you have of it. And so we just arbitrarily say all solids are going to have a concentration of 1, and that will be taken into account in the K. Right? If it weren't 1, if it were some other number, right, then that just means the value of K would be different. Right? So when we actually measure the value of K, it's assuming that we're just going to use 1 for a solid. Okay, same thing for a liquid, you have a pure liquid. Okay? So does it matter whether you have 1 milliliter of liquid or 10 milliliters of liquid? Does it matter what the concentration, will the concentration be different if you have only 1 milliliter compared to 10 milliliters? No. They'll have the same density, the same moles per volume. And so what do you suppose chemists have decided to call the concentration of liquids, pure liquids? 1. Yes. So the concentration is equal to 1 for a pure liquid. All right, for a gas. Now, the standard state is 1 atmosphere for a gas. Okay? Now, if this happens to be a gas, if D happens to be a gas, is it always going to be 1 atmosphere? No. So what we would put in that, let's say it happens to be 2 atmospheres. Then what we would do is we say, all right, this concentration is a ratio of the actual pressure, actually I should say that No, all right, so we're doing a case of P. It's the actual pressure divided by its standard state. The units cancel, so there are no, since the standard state of a gas is 1 atmosphere, if it's 2 atmosphere divided by 1 atmosphere, then that means that concentration is twice what the standard state pressure is. And so we would just put a 2 in there. Would we put the units in there? No. These things don't have units associated with them. But that also means you have to use the right unit when you plug that in there. In other words, if I have a gas and it's 300 torr, can I put 300 in there? No, because what's the standard state unit? Atmosphere. So that means whatever you put into that has to be in atmosphere. Now, when a gas is acting as in this, then we can put in moles per liter. It turns out case of P is always used by real chemists for problems. But we will say that if you have a case of C, then you put the concentration, treat that just like a solute and put its concentration in moles per liter.
Can you just try like focusing or something? It's hard to see.
Yeah. All right. So those are the standard states we've done so far. Okay. Now, for a solvent, right? So you got some kind of solution. You're adding some solute to the solvent. The solvent has a standard state that is its mole fraction. That's what the standard state of a solvent is. So we are going to use dilute solutions. All right. We're always going to assume dilute solutions. So what is normally the mole fraction of a solution that's very dilute for the solvent? Let's say I put 0.001 moles of sugar into 1 liter of water. Right? So my molar concentration is 0.001 molar. That's a very dilute solution. Anybody want to guess what the mole fraction of that solution would be for the solvent? It would be 0.9999 something, right? It would be very close to 1, right? So for dilute solutions, we're going to assume a mole fraction of 1. So whenever you see something acting as a solvent, then its activity or its concentration is simply going to be 1. Now, real chemists in real problems would take into account the mole fraction for more concentrated solutions, right? So if it's 0.95 or 0.90, but for our purposes, we're going to make some simplifying assumptions and assume that we're using dilute solutions where the mole fraction is going to be very close to 1, and so have a very minimal effect on any problems that we do. And finally, the standard state for a solute is 1 mole per liter. All right. So if I have a solution where I've got a solute, let's say A is a solute, right, and it's got 0.5 moles per liter as its concentration, what would I put for the concentration here?
1.
Nope, I wouldn't put 1. That's the standard state, and it's not at its standard state. It's at 0.5 moles per liter. So I wouldn't put 2 either. I would put 0.5, but I wouldn't put the units, right? It would just be 0.5 molar relative divided by the 1 molar gives me just a unitless number of 0.5. Right? So now I'd have to make sure that the concentration I had was in moles per liter. So we've seen some other concentrations. If you have a 0.1 molal solution, would you put 0.1 in that right there? No, you'd have to first figure out what the concentration is moles per liter. Is that possible? Is it possible to convert from molality to molarity? Yes. Hopefully you realize that's a learning objective. You need to be able to do that to then put that into the equilibrium expression. All right. So what about the value of the equilibrium constant? Oh, wait, no, let's not do that. Let's actually pull out that worksheet and apply what we just did, and then we'll talk about numerical values, and then we'll quit for a minute. All right, So, and take the quiz, of course. The average on the quiz for my first section was over 90%, right? So it is not a difficult quiz if you're familiar with the lab. All right, so in fact, I think I had 4 people out of 20-something got less than 90%. Everybody else got 90% or above. Yes. All right, so this is what's sitting in front of you, hopefully. We want to come up with the expressions for K sub C and K sub P. All right, so here we've got 2 gases, a liquid, and a solid. Okay? So it's products over the reactants raised to their coefficients. But what do we know? So it's products. What do we know about the concentration of that liquid? It's 1 molar. We just leave it out. Now, here we've got the concentration of carbon dioxide, which we would then raise to the 3rd power. Here we've got a solid, which has, it's called unit activity. So we just leave that out. And so we put carbon monoxide to the 3rd power. And so there's the proper equilibrium expression for that chemical reaction right there. And K sub P would just be replacing any gases with pressures. So this would be the pressure of carbon dioxide cubed divided by the pressure of carbon monoxide cubed. Okay. All right, calcium carbonate decomposing into calcium oxide and carbon dioxide. What would K sub C be here?
Just CO2.
Just the concentration of CO2. That is correct. In case of P,
Pressure of CO2.
would just be the pressure of CO2. And finally, magnesium phosphate ionizing to form magnesium ions, or dissociating. Dissociating to form magnesium ions and phosphate ions. So here we've got a solid. And then what are these things called?
Aqueous.
Solutes. These are solutes. So be the concentration of magnesium cubed and the phosphate squared. Okay, now oftentimes people have trouble with the K sub P here. Yes, Riley?
I was just wondering if
Oh.
you could, sorry.
Oh, it's cloud cover is moving again. Okay. What do you think K sub P is in here? We don't have any gases, so what is K sub P?
Concentration.
Yep, it's just the concentration of magnesium ions cubed and phosphate ion squared. When there are no gases, K sub P and K sub C have the exact same expression. If there are gases, then you just replace whatever concentration there is with the pressure. And finally, what does the numerical value of the equilibrium constant tell us? If something has a very big equilibrium constant, indicates one thing about a reaction. Something has a very small equilibrium constant, it tells us something else. Let's say we have an equilibrium constant that's a very small number. What does that mean about that chemical reaction?
It has a small reaction.
It will be mostly reactants, and hardly any products will be formed. Small numbers, 10 to the minus 10th, 10 to the minus 15th, even 10 to the minus 5th, result in very little product forming. Big numbers, 10 to the 5th, 10 to the 10th, 10 to the 15th, right? That means almost all of the reactants are consumed, and what's primarily present is product. Almost all of it gets, all of the reactants get converted into products. So we have 3 reactions here. HCl decomposing to form hydrogen chlorine. Are you going to have mostly reactants or products after this has reached equilibrium? Reactants, right? So the magnitude tells us 10 to the minus 17th being a very small number, hardly any of the HCl is going to decompose. All right, if we have a mixture of sulfur dioxide and oxygen together, right? once that reaches equilibrium, are we going to have mostly reactants or mostly products?
Product.
Products, because that is a very big number, 10 to the 9. All right, so we're going to have mostly SO3. Finally, we have nitrogen and oxygen together in a room like this. What can we tell about that chemical reaction? It's going to be primarily reactants. That's a good thing, because do we have primarily nitrogen and oxygen in here? Right, 20% of the air is oxygen, 80% is nitrogen. All right, so if this had a big K, then it would all be converted into NO. And if you're familiar with NO, is it good to be breathing in a lot of NO?
NO.
No, that's a toxic, no for NO. It's a toxic gas. We'd all die of poisoning. Right? So if this chemical reaction had a large equilibrium constant, then life as we know it would not exist. There would have to be some other form of life, but not the way we have seen it. All right, I'm done.